both Tim Moon and Gavin Brown, who are both at the University of Manchester, where I completed this work as part of my PhD. Okay, so the problem we're starting off with is one of high-dimensional data. So in numerous machine learning applications we encounter in the real world, we have extremely high-dimensional data sets, and this includes cases from computer vision through to genome analysis. And this gives us both statistical and computational problems. But the key thing is that whilst this data itself is very high-dimensional, the actual distribution that the data lies on might have some intrinsic structure, such as lying on or close to a low-dimensional manifold. And the question is, how can we best take advantage of that? So one very widely studied approach to doing that is called dimensionality reduction, and particularly unsupervised dimensionality reduction. And this applies whenever you've got data that lies on some low-dimensional submanifold within the high-dimensional feature space. Essentially, you want to learn a mapping which somehow unwraps the structure by compressing to a lower-dimensional space. Now, in this talk, we're going to do something a bit different, another form of dimensionality reduction, where we employ modular dimensionality reduction. And the underlying hypothesis here is that multiple complementary representations of the same object can often provide more information than a single low-dimensional representation. So this is our underlying hypothesis. So what do we want to do? Well, usually in dimensionality reduction, you have some mapping from a high-dimensional feature space to a low-dimensional space. But here we want to perform multiple low-dimensional mappings to lower-dimensional subspaces. So I want to contrast this with multi-view learning. So this is not multi-view learning, where you have multiple different views on your data set, say coming from an image and some coming from audio, and you try and form one low-dimensional representation. What we're doing, in a sense, is the opposite. We have a single high-dimensional representation, and we're finding multiple low-dimensional representations which each perform well and can be used in parallel. So how do we go about doing this? Well, our starting point is going to be an approach to dimensionality reduction via what's called the inner product loss. And the key thing with the inner product loss is that a lot of geometric structure in any setting can be encoded through inner products. So a natural approach to doing dimensionality reduction is to try and preserve inner products in the low-dimensional feature space. So let's say we take an unsupervised data set, D, and we're trying to learn a mapping phi to a low-dimensional feature space. And what do? We try and minimize this inner product loss, and that's just the mean squared error of the inner products in our feature space, in our representation space, taking a target as the inner products in the original space. And this is actually turns out to be quite general, so numerous instances occur in the literature: PCA, kernel PCA, isomap, locally linear embedding, and others all occur as minimizers of this inner product loss function. Now what we want to do in this talk is learn multiple low-dimensional representations. So what we're going to do, we're going to use a modular inner product loss. And the way this is constructed is as follows. So again, we have an unsupervised data set D, and we're going to learn a sequence, big phi, of low-dimensional representations. I'm going to call each of those phi n. And each of these is a mapping to a lower dimensional feature space. And our loss function is going to consist of two components, the first of which is the average inner product loss. So we're going to look at the inner product loss we saw before and simply take the average over the different modules. However, if we purely minimize that, then all of our modules are going to look very similar because they're going to be doing the same thing. And what we want is our modules to be, in some sense, complementary. So we want them to be different from one another. So what we're going to do is look at a given pair of feature vectors and compute the inner product for each of our modules of that given pair of feature vectors, and try and encourage a high level of variance in inner products over our different low-dimensional embeddings. So we've got two components, the average inner product loss and the variance of the different inner products. And we combine these in what we call modular inner product loss. So it's got two components, as I said, the first of which is going to encourage faithful representations of the data, the second of which is going to encourage a diversity of representations by promoting a higher level of variance in our loss function. And to control the trade-off between the two, we have what's called the diversity parameter, and this simply tells us what level of emphasis we're placing on a diversity of low-dimensional representations. Okay, so if we take a look at this loss function, the question is, how do we actually minimize it? How do we obtain our low-dimensional representations? One thing that we can do straight away is observe that it's actually a differentiable loss function. So an obvious approach would be to employ some gradient-based solver, such as stochastic gradient descent. And the downside of pursuing this approach is that if we look at the summation in question, we're actually summing over all possible pairs of examples, and this can make our optimization extremely slow. So we're going to try and do something more efficient, and what we employ is a fast optimizer, which we call the module by module algorithm. And the way the module by module algorithm works is actually quite simple. Essentially what we do is we freeze all the modules but one, we freeze their parameters, and we perfectly optimize that module. And in this setting, that's made very efficient because we can employ techniques from spectral theory to obtain an exact solution once the other parameters are fixed and perfectly optimize that module. We then move on to the next module, perfectly optimize the parameters of that module, and move on, so on and so forth. Okay, and we perform iteratively until we reach some form of convergence. And this algorithm has some nice properties. The first of which is that it's guaranteed to reduce the loss at every iteration until a critical point is reached. So we never increase the loss. And the second nice property is that it actually performs very well in practice. So if we compare it with stochastic gradient descent, we get a performance speed up of around 10 times. And if we compare it with something like the Adam optimizer, which is very fast in a lot of settings, we get about 3 times speed up. But perhaps even more importantly, we don't have a learning rate in this algorithm, and that means that we don't have to tune the learning rate. So whereas if you're employing something like Adam or SGD or one of these corresponding algorithms, you're going to have to do a lot of trials and find the best learning rate. For this setting, you don't need to tune the learning rate, so that creates a dramatic speed up in our particular setting. Okay, so we've introduced the modular inner product loss, and we've found an efficient approach to optimizing that modular inner product loss. And now what I want to do is compare the modular inner product loss with other reasonable approaches to pursuing modular dimensionality reduction for some sort of parallelization gain. So we're going to compare with a number of appropriate baselines. So the first of which we call bootstrap, which is where we do bootstrap samples of our data and just simply apply kernel PCA to each of the different bootstrap samples. So here we're trying to promote diversity simply by taking bootstrap samples. The second of which we call partition, is where we produce a very large number of kernel principal components and simply randomly partition those kernel principal components into discrete submodules. Thirdly, we have random, which is essentially just performing random projections of our data set. And finally, we're going to compare with what we call MBM, which is our approach where we minimize the modular inner product loss with this efficient MBM algorithm. So we're going to compare on 2 tasks, the first of which is an image retrieval task. We're trying to find images which are similar to our own in an efficient way. So how do we do this with modular dimensionality reduction? Well, we compute multiple low-dimensional representations of our image, and then for each of our distinct low-dimensional representations, we separately, in parallel, compute nearest neighbors. We then take the image, or collection of images, with the lowest average distance, where we average over the different modules. Okay, and what we observe is that if we place sufficiently large emphasis on diversity, we actually get quite dramatic performance boost over the comparable baselines. So the second task we considered was classification, and here pipeline is similar. We again compute multiple low-dimensional representations of our data, and then for each of these different representations, we in parallel train and classify. And then we simply put a test feature vector in, and to send it to each of our different modules, and take an output and ensemble those outputs, so take the average output. And again, we have quite a dramatic performance boost by employing this modular inner product loss-based approach. Okay, so we produced quite a few different experiments, and you'd be very welcome to see some more of those at the poster session. So I want to close by talking about quite a surprising connection we found with this and this approach here, which is modular dimensionality reduction, and what's known as the dropout algorithm in deep learning. So As many of you will know, Dropout is a method for deep learning developed by Hinton co-authors, and essentially it's a regularization approach whereby you're training a deep neural network, and as you proceed with your stochastic gradient descent, at subsequent iterations, you randomly choose to keep a subset of hidden nodes with some fixed probability, and complete the forward pass, complete the backward pass, and move on to the next time step. So let's look at the analog of that in the dimensionality reduction setting. So let's suppose you're trying to train some dimensionality reduction module, a single dimensionality reduction mapping, and you're using the inner product loss, and what you do is you randomly drop subsections of your low-dimensional representation. You complete your forward pass, complete your backward pass, and proceed on to the next update. So it's a direct analog of dropout deep learning. Well, it turns out that this actually has a strong equivalence with our approach of modular, based on the modular inner product loss. And that equivalence essentially is that for any given choice of probability P of keeping a module, this translates into a particular value of the diversity parameter, of amount of emphasis placed on diversity. And if we choose the right combination of probability and diversity parameter, we actually get precisely the same gradient updates in expectation. And we can see this here if we look at dropout-based algorithm and compare with the modular loss trained with stochastic gradient descent, we get a very similar trajectory during training. Okay, so to conclude, we've introduced the modular inner product loss, which is designed for extracting multiple complementary representations of the data. We've then proposed an MBM optimizer, which is guaranteed to decrease the loss until a critical point is reached. And it also provides a significant speed up over other gradient-based solutions, and there's no need to tune the learning rate. And finally, in addition, we found some rather dramatic improvements over a number of baselines in image retrieval and classification tasks. We've also found a rather surprising link to dropout. So, thank you very much for listening.
Any question? Okay.
Okay, thanks for the talk. First of all, clarification. Is capital M fixed, or you add modules as long as they're useful? And let's say, based on this, basically, whether you try to get some understanding of what each of the low-dimensional representations catch of the underlying data, for instance, from the images. See what I mean?
Yeah, so this is, really, it's a good question, especially with regard to, so choosing M. So in all of these experiments, M is fixed. And essentially, the way we're seeing it here in this paper is, it's constrained by, we've got computational constraints. You've got a number of nodes for computational reasons, and that's kind of your budget. But it would be interesting to see what happens if you can essentially attempt to learn M. Maybe you have some, you know the cost of M, and you know that adding modules is going to help you. Adding modules helps always, but potentially there might be some trade-off between cost, and you might want to learn it based on that. So that would be a really interesting research avenue, which we haven't properly pursued yet. And with regards to trying to understand what these different modules learn, essentially this turns out to be extremely challenging. We kind of looked into a couple of approaches. One approach was kind of heat map based. We didn't actually find anything too significant based on this approach, but if you look at things like confusion matrices in classification tasks, you can see that essentially different modules will have different weaknesses that become transparent in the confusion matrix, and that's kind of the most significant thing we see so far.
Another question?
Hi, thanks for the talk. I was wondering when you showed the experimental results, there is this very surprising drop when you set lambda to 1. So can you give some intuition there why this happens?
Yes. So sorry. So essentially what's happening here is, and there's some more details on the paper in this, is that if you actually investigate the loss function, so this phenomenon actually comes straight out of the loss function. So when you take lambda to be equal to 0, you can see that actually these modules are all going to be identical, and that's quite transparent. What's less transparent perhaps is that if you take lambda to be equal to 1, then you actually end up with just the same objective, the inner product loss, but for the entire representation concatenated. So what that means is you've essentially got the equivalent loss function that you would have if you just did kernel PCA down to m times k principal components. And now if we turn to the results of the experiments that you notice, this sharp drop-off, this is coming from that. So essentially what's happening is when you reach 1, you have this sharp drop in performance because you've placed too much emphasis on diversity. And in essence, you've got orthogonal directions you're mapping to, and that means that many of your modules are not going to faithfully capture important structure in the data that's needed to perform the classification task. So essentially, it's too much diversity. That's what it is.
Okay, yeah, thank you.
Other questions? Okay. We thank again the speaker. So now